umbrella that doesn't rely on traditional materials to keep them dry, but instead creates a force of air which is so strong it actually deflects the rain away from the area above you. And talking of air, you might want to take a look at this. Because watching a hawk take on a drone for invading its airspace
that's interesting.
gets old.
Well, I've never seen one of those umbrellas actually in use. That's kind of cool. I guess it's a bit antisocial because it probably blows all the water on someone else. And so, what else have we got? Oh, yes. Bit of death.
Northern California, a giant fireball there last night, just around dinner time.
Not tonight.
Dozens of homes destroyed after a huge explosion last night. It was apparently caused by a broken gas line. It happened in a San Francisco suburb very close to San Francisco International Airport. Priya David Clemens is at the scene in San Bruno this morning with the latest. Priya, good morning.
Erica, good morning to you. We're right at the edge of where the fire stopped. I want you to take a look at this devastation behind me. You're going to see burned out cars. The firefighters still working to make sure all the smoldering flames are out completely. We're seeing little pockets of flames still pop up here at raging inferno around dinner time Thursday evening. Flames roared some 60 feet into the air as block after block in this residential neighborhood, about 5 miles from San Francisco's airport, were engulfed. Witnesses reported hearing and feeling a large explosion, leading to early speculation that a plane may have gone down.
It sounded like a jet, almost, like just a giant roar, and then the biggest boom I've ever heard in my life.
But it was a hot...
So we looked on the first day or second day of this class at a map of all the gas, natural gas and gasoline pipelines going around the country, and they're quite dense. And there was a plan actually to bring, when the coal plant, which sits on Burroughs and College, steam plant, I guess, was transferred from coal to natural gas. They're going to bring the gas pipeline down Burroughs Street, and all the residents objected because presumably they didn't want their houses incinerated, was the main reason. So it came through and across campus. And so it's much more expensive, but that's the solution to it. So this was one in San Bruno, just west of San Francisco Airport, south of San Francisco. And so pretty safe ways of doing it, but not 100%. Nothing is 100% safe. I don't know if this is... that's not going to work. So the Keystone XL pipeline, I can't remember the fate of that. That was a big political battle in getting tar sands oil from Alberta down into the refineries near the Gulf and going across the sand dunes of Nebraska and Native American land, and it became a big political deal during the previous Trump administration. Not sure what this is. Perhaps that doesn't work. And then this is Gateway Pipeline. I want this. This is probably worthwhile watching as well. And again,
2013, at about 10:50, carrying petroleum crude oil in 72 Class 111 tank cars arrived at Mount Quebec. In keeping with the railway's practice, the locomotive engineer parked the train for the night on a descending grade on the main track. After shutting down 4 of the 5 locomotives, the engineer applied 7 handbrakes. Railway rules require that handbrakes alone must be capable of holding a train, and this must be...
So this is a tale of woe in Canada. So about shale gas and shale oil. It maybe kicked off around 2005, 15, 20 years ago now. The Pagula hockey arena Pagula made his money on shale gas. I think $6 billion. Was a graduate actually of the petroleum program at Penn State. And so it's made the U.S. self-reliant, or North America self-reliant for hydrocarbons, even though we're trying to transition from it. And so one of the regions where it comes from is the Bakken in North Dakota. And the Bakken reservoir, shale oil, is quite volatile. And of course you could transport it from central U.S. to the refineries on the East Coast by pipeline if one existed. And the other alternative is to take it by train. And so you see these black tankers sometimes in the siding over by the Nittany Mall, by the penitentiary, state penitentiary. And this was one such train going across Canada, Quebec, one of the eastern provinces, parked above a town called Lac Mégantic overnight, put the brake on, or thought they'd put the brake on. But for whatever reason, it loosened up in the middle of the night with no one on board, and the train started rolling into town. So this is the animation. It's kind of the post-mortem of the evaluation of what happened. And it was just a tragic problem that the brake came off over time. The truck, the carriages and all the tankers rolled into town. Everyone was at the bar on a Friday night, Saturday night at 10 o'clock, 11 o'clock at night, and devastated the town, killed 50 people or so. And so I guess if you have hydrocarbons and you want to transport them across the country, perhaps using pipelines is not a bad deal. So rare events and tragic events, but events nonetheless for these. So anyway, that kind of brings us up. So pipelines. So we tend to think about pipes in our house, but of course pipelines are used for all kinds of things. And of course well bores for getting water out of the ground, and for getting natural gas and hydrocarbons out of the ground are also pipes of some nature as well. So that's what we're busying ourselves with now. So what did we talk about last time? Okay, we tried to motivate the idea of, I guess, I'll go back maybe to drawing things again today. And so we made the point yesterday of kind of what we've come through. We talked about Bernoulli, and we've talked about the energy equation, and the only difference between them is that if we use the energy equation, it allows us to realistically accommodate losses in our system. So I'll get back to drawing things. And we talked last time about how we can characterize these flow systems. And I guess we could do it in terms of what we know about this. This is just a simple geometry that we have, which would be, I guess, this would be relative to our datum. So z equals 0 here, and z going upwards. And we've talked about Bernoulli. This would be z1 minus z2, delta z. So yeah, you'll remember that our Bernoulli equation is elevation plus pressure head plus velocity head plus pump head, and that is equal to the converse on the other side, which you also know, probably don't have to say. And added to these are two other terms, sum of, well, let me do it on the same line, they'll both fit, plus the sum of head losses plus the sum of head losses. And these we'll call major, and these we'll call minor. And so if we remind ourselves of this, you know all these features, I think. This always has to be upstream. And corresponding, this has to be downstream. Pump head we define as equal to the power output. We'll call W dot divided by density times flow rate times G, gravity. I guess we've also called it other things such as, I guess Q rho is the mass flow rate, right? We called it uppercase M and G would be one way to write it. We know if it's positive, it's a pump. If it's negative, it's a turbine taking energy out of the system. So that's our sign convention for these. We know this is downstream, and so we also know that these components, we haven't completely defined them yet, but we've alluded to what they are. Head loss major are for losses in the pipe, so they'd be along the length of the pipe, and it's given by a friction factor, a length of the pipe divided by its diameter, and multiplied by the velocity in the pipe squared over 2g. So this would be V, this would be D, and this would be L, if we're doing that. And so if we can find a way to be able to figure out what F is, then we can, if we know the velocity, we can calculate what that loss would be. And the minor losses would be losses which are given by something like head loss is equal to a loss coefficient, which is often called K sub L, times V squared over 2G. So you notice that in both of these we have this velocity head term, and it's multiplied by something. In one case it scales with the length of the pipe. Longer the pipe gets, you double the length of the pipe, you double the head loss, so it's a linear system. And this represents losses in fittings, in fixtures. So when you go from being in a static tank to accelerating the fluid into the pipe, then there would be a loss at this. So we'll talk about that in more detail later. But for now, you just need to realize that there are two forms of these losses. And these would be minor losses. So I guess what we could do is we could write these equations in terms of a point 1 and 2. And if we did that, I don't know where my green has gone, then we'd end up with pressure 1 is 0, pressure 2 is 0, big tank, velocity 0, downstream velocity is 0. They happen. We've only got a pipe, so we'll ignore this. So we'd end up keeping this, and we don't have a pump in this case. So if you don't have a pump between the upstream and downstream, you don't need to include it. It would be 0. That's relevant to the third question on the tests. So you'd be left with just an expression here that you want to solve, which would be Z1 minus Z2 is equal to HL, which is, and there's only one HL, so it's equal to the friction factor times the length over diameter times V squared over 2G. V squared wouldn't be 0 because the velocity in the pipe. Notably, I guess, you could see that if this was Bernoulli and there was no head losses in the system, you couldn't sustain this, right? Because it would give you Z1 minus Z2 is equal to 0, and that's not true. So the whole essence of this problem is the frictional losses you incur in the pipe. The alternative way to do it, that would be one way to do it. A second way to do it would be to write it with points, instead of points 1 and 2, maybe with points 3 and 4. And 3 and 4 could be here. And I guess if that's the case, I can erase these straightforwardly. This would no longer be 0. This would no longer be 0. But this would, because they're on the same elevation, right? It's not 0, but they cancel out. 3 and 4 on the same elevation, so we lose these. I guess in our way of drawing it, I guess I'd have done it like this, right? Not 0. They're equal to each other. And so if that's the case, then we have P1 over gamma minus P2 over gamma is equal to HL. And of course, the pressure here is just going to be equal to whatever this height would be. Well, the upstream pressure is going to be this, which is just P3. And so P3 is equal to H. I don't want to call it Z, right? Is H3 gamma W. So either way we do it, the velocities cancel out if the pipe is the same diameter along its length. And so we just need to figure out exactly how to work out these characteristics. Yeah.
For equation 1, how come we don't include the minor losses?
Can't, because I don't want to. Yeah, let's not complicate matters. They're minor, so we don't want to. So for what we'll do today, we'll concentrate on minor losses maybe next time, but we'll talk about, this is probably these are the major components of losses, hence they're small incrementally, but they're major because they act over long length. So just forget about it for now. And so what we could do is we can then hark back to what we talked about last time. And so hopefully you've still got 15 hours to look at 9.3. But remember last time we used Buckingham pi. We described our system in terms of flow in a pipe, which is what we're doing. I guess I'm making the point that we could pull this pipe out on its own, just like this, and we could just look at the pressures upstream and downstream. And so we could look at the pressures upstream to downstream. So this would be what we call dP, I guess, on Monday. We could look at the length of the pipe. We could look at its diameter. We could look at the fact that fluid is coming out of it at some average velocity. I'm not sure we made the point last time, but if we looked at a section across this, the actual flow section will look like this in terms of velocities. But what we typically do is we take this and we transform it to be a uniform velocity, that is this. And so in that particular case, the area under the curve on this parabolic distribution is equal to this. So this is the velocity. I suppose this is velocity as a function of radius. This is also. But this velocity here is what is just an average velocity. So what else did we say? We said that we would have in this density of a fluid, we'd have a viscosity of a fluid, we'd have a velocity, I think that was it. Oh yeah, and we might also have a roughness, right? And that roughness we characterize by some amplitude epsilon. So we said something like we have the pressure is some function of these terms, which are density, could have gravity in there, but we don't need it, viscosity, length, diameter, roughness. Should have put velocity up front. So there are 1, 2, 3, 4, 5, 6, 7 terms here. From Buckingham pi, we know that if the number of pi groups equals the total number of terms, 7 minus the total number of MLT, mass, length, and time are represented. So certainly mass is represented here, as is length. Time is represented in velocity. So we have all three. So 7 minus 3 is equal to 4. And we said last time that we could describe this behavior in terms of 4 dimensionless groups. we can take care of 3 of them by noting that these are all in dimensions of length. And so we could just combine 2 of these as Buckingham pi. You don't always get you'll always get dimensionless groups, but you don't get necessarily the dimensionless groups you want that guarantee that you can use it usefully. So it helps to know what those are in advance. So if we use these, we end up with dimensionless groups, and that is that an Euler number is equal to some function of a Reynolds number and length over diameter and roughness over diameter. So we know that there are 4 groups. We can combine them in some way. If we did it in a smart way, we'd end up with this. If we want to write this out in longhand, we'd end up with an Euler number, which is a pressure, which we've called change in pressure, divided by rho v squared. Remember, when dimensional analysis, dimensional similitude, the model has to look like the plane when it's shrunk down. Kinematic similitude has to satisfy the Reynolds number. And the Reynolds number is going to be something like a velocity, a density, a characteristic dimension, and a viscosity. And these 2 other terms, L over D and relative roughness. And so what we could do with that is that if we think that these relate to each other, if we take a pipe that has a given length and diameter, and let's say the roughness is 0, then we could do an experiment on that pipe. And if we then plotted from that experiment these 2 remaining variables, so the pipe doesn't change, the roughness doesn't change, it's just a single pipe. And so we do an experiment flowing fluid along here under a particular pressure gradient between upstream and downstream, and we measure the velocity, the average velocity. So if we did that, then we could plot pressure over rho v squared, which is the Euler number, and against the Reynolds number, which is the velocity, the density, the diameter of the pipe, and the viscosity of the fluid. If we're only using one fluid, then the densities and the viscosities will be the same. And so if we do that at a given pressure, we'd get a velocity. So P dP1 gives us V1. And so that would give us a point which we could plot on this graph, which would be this. Very simply, we get this. And so then what we could do is we could double the pressure and measure the velocity, and this would be just 2 dP2. So in other words, I suppose we'd be doing this simply. So this would be dP again on top of it, so just double it. And so you might think that if you double the pressure, you could think that if it's linearly related, you might think you double the velocity. And so maybe this is double, but maybe it's not quite double. Let's assume it is double. So you've doubled the pressure, so you'd think to plot up here, but you've maybe doubled the velocity, so you've quadrupled the velocity, so the Euler number would be less. And so if you plot that, it would plot here, maybe. So this would be for P2, and this would be for P1. But if you've doubled the velocity, then this number would have increased. And so you'd have a point that would be here. And so now, if you want to do other experiments, you'd expect all those other experiments to just go on those lines if you change the pressure. If you increase the pressure some more, maybe you'd be down here, and you've got a relationship. And so this starts to look like the behavior that we'd expect. And so we can characterize the behavior in terms of this. And actually, this is exactly what we expect to see. The so-called Moody chart is that this curve here is just from doing the experiment at one pressure drop, doubling the pressure drop, tripling the pressure drop, and you just move down. And so without knowing anything about your system for a particular pipe in a particular flow regime, low enough Reynolds number, you can get that experimentally. You could also come back here and you can keep on doing that. So you could do it at P4 is equal to 4 dP1, say. And you might expect that this keeps on going, but actually what you'd find is that it starts scooting over here. So it'll come down here, and you get a change in behavior. And you see that in the Moody curves that we just looked at. So if you keep on doing it to get P3 and P4, then you don't get this linear relationship anymore. You don't know that yet, but we'll explore why that might be. But you come along this. And this occurs at a break in the behavior. And typically this is at a Reynolds number of something like 2,200 of that order. And so you see it on here, that this is this. It's not quite as clean as that. It doesn't quite scoot over, but you see it's kind of going over here. And you see that now this Euler number, which is this thing here, the Euler number is also what we call this friction factor. You realize that this number in, where is it? This friction factor here is actually our Euler number. It's the amount of pressure that's eaten up in pushing fluid along a pipe. So if you're pushing fluid along a pipe, it starts off a high pressure here, comes out a low pressure. So this pressure is eaten up, in this case, because there's a drag along the sides of the pipe. It's just a shear force due to the viscosity. If it's a closed pipe and the fluid's hitting the wall and going around it, it's just the same thing. Pressure is high on the front end of the pipe, it's low on the back, and so there's a net force on the pipe. It's just from flow around the pipe in that particular case. But it's the same basic relationship. And so that's the kind of behavior we have. So we'd like to be able to understand a little bit about how we get these relationships. So the other thing we could do this all experimentally, which is what we've done here, or we could be a bit more flash about it, and we could do it analytically, I suppose. And if I go back to something I think you've seen already, I need to keep the pen away from this. So in week 8, it should be right here. I don't know how much time we spent doing this, but yeah, well, can't remember whether we talked about that this year or not. You'll remember, also relevant to this course, but not really examinable material, is that, so you remember that we had conservation of mass, which we wrote as being, in this particular case, sum of mass flow rates are equal to 0 if we ignore the other terms. And we have conservation of momentum. I'll write it in shorthand, mv. And you'll remember that that was a velocity multiplied by a mass flow rate. You used it on your test last Friday, is equal to a force. You'll remember that these are velocity as a vector, so there's 3 equations here. One in x, one in y, and one in z, and just one for this. If you take each of these equations for control volume, and you write those equations for control volume that is a little differential element in our coordinate system, so x, y, and z, so this is x, y, and z. Not going to derive it for each of those components. Then this would be, for instance, this would be Vx. So if you take these equations and write them out in differential form, where this length here is a length dx, and this length here is dy, and this would be dz, then you get what are called Navier-Stokes equations, after Navier and George Stokes, French and British mathematicians. And these are the equivalent of those. We end up with 3 conservation of mass equations. This is the v squared over 2g term. So you remember they're just like Bernoulli equation. This is v squared over 2g. This is, no, sorry, that's not it. It's not. This is v squared. This is v squared over 2g. This is p over gamma. This is elevation. And this is head loss, if we're writing in terms of Bernoulli. We'd have a Bernoulli equation in the x direction, a Bernoulli in the y direction, and the z direction. And I guess the only point I want to make is that at each of these little differential points, we'd have 3 unknowns. We'd have velocities, vx, vy, and vz. And we'd also have a pressure in here. So we'd have 4 variables. So if we want to solve a flow system that involves these, we have to have a total of 4 equations to solve them. So we have 4 conservation of momentum equations and a conservation of mass equation. This is just a different way of writing it. So it's basically these equations. This equation, of course, has to have a head loss term in it, so it's not really conservation of momentum. It's actually the conservation of energy term, which we dealt with in week 8, but it's very similar. And so we can solve these equations. If you solve these equations for some seemingly esoteric problems like flow between 2 parallel plates, which is like flow in a duct, you get a distribution of the pressure across the duct and a very simple relationship, ultimately, I won't go through derivation, that says that the average flow velocity is equal to 2 times the half thickness of the duct. I'm just going to write out this, squared the pressure drop divided by 12 times the viscosity. And so the geometry of this is given here, so that this is the duct, this is to be, or not to be. This is the width across it, and you get the average velocity coming out of this. It's not completely esoteric. If you're petroleum engineers or environmental systems engineers and you know what Darcy's law is, it gives the flow velocity in porous medium as a function of a permeability, a viscosity, and a pressure gradient. Then you can link, I'm going down a rabbit hole, I know. You could link the flow across a system, say an aquifer that looks like this, that has fractures across it, where these fractures have some kind of aperture B, and you can get the equivalent permeability of that as being equal to B cubed over 12S. S is just the spacing between individual fractures, sets of fractures. So these would be 2 fractures, and they'd be separated by some distant S. So not completely esoteric. You could use this to calculate permeability of a gas shale reservoir or a fractured reservoir that you're containing your radioactive wastes in. Likewise, you can use those equations to get magnitudes for flow within a pipe. And the solution for that is this. And again, I'll just write it out. Perhaps I'll write it out here. And so in other words, the velocity is equal to this term here. So I'll write it out differently. I'll write it out as the diameter of the pipe squared over 32 times viscosity times the pressure gradient. maybe I will try and copy that. And so that merely represents flow within this pipe. And so we're interested, we have a velocity profile across the width of this pipe. You'll notice that it's anchored, hopefully I can still write that. It's anchored at 0 velocity at the walls of the pipe, maximum in the middle. It's actually a parabolic distribution. This is the distribution. But as I said before, we're kind of interested in the average velocity. So if you take the area of that pipe and you reduce it so the areas of these two prisms or two shapes are the same, then this would be the average velocity here. This is the actual local velocity. It changes across the radius. And this would be the radius. We already drew this. All right. So again, I'm getting bogged down in a bit of a rat hole here, but it's fine. Humor me for the moment. So I tried to get back where we were. Bless you. This is probably where we are here. So we're talking about pipes. And so let's see if this still works. It might have forgotten already. No, it didn't. Excellent. Yeah. Okay, right. So we want to represent this. Yeah. What we'd like to do is figure out whether we can get an actual parameter. Oh, that's a bad choice of term, isn't it? This should be function of. This is not that term. Function of. We'd like to figure out exactly what this friction factor is for a pipe. So what am I going to do? This is the average velocity, which is given by that. And so I could write this also for our geometry here. This is dP over L. Well, same geometry as before. dP. This is L. So we could write this as average velocity is equal to diameter of the pipe squared over 32 times the viscosity times the pressure drop over the length over which it drops, which is L. And so that is equal to, we know that head loss is equal to dP over gamma, right? In other words, or dP is equal to head loss times gamma, just from the relationship. And so we could define this here as that. And so this would be that the velocity is equal to d squared over 32 mu head loss times rho g, just to write these terms out, divided by length. And so if I wanted to write that in terms of head loss, I could as head loss is equal to velocity times 32 times viscosity over d squared. Times length over rho g. And I think I want to multiply that by 2 over 2 and v over v. Right? This is just 1. And the reason I want to do that is because now I want to split it up into terms that mean something to me, or us perhaps. So if I take this and multiply by this, this is 64. Sorry. This is 64. This is L over D. This is V squared. So this and this did I lose a P somewhere? No, I got rid of it. This is V squared over 2 G. And I'm left with, if I'd use a different color, mu d rho v. So mu over d rho v. So what we've got exactly here is that this is equal to 64. This term here is Reynolds number, but 1 over. And this is length over diameter. And this is v squared over 2g. So in terms of how we defined this before, I did actually get it out. This is friction factor. This is length over diameter. And this is v squared over 2g. So if you remember, we came into the class today just throwing this out, but not really explaining where it came from. But that's where it comes from. And so this is for laminar flow. And so what we mean by that is that the flow profile across the width of the pipe is this parabolic flow. No vortices, no eddies, but this particular distribution which gives us this. And so this is useful because this friction factor, F, is just equal to 64 over Reynolds number. And we also said that this friction factor, or perhaps I didn't, is also equal to EU. And so if we go back to this, this is also equal to our friction factor. So I'm just trying to make sense of where all this comes from. You don't need to know those derivations, you just need, it's perhaps useful to be able to understand where it comes from. So we could do experiments, and Buckingham Pi allows us to choose groupings of variables that allow us to do the minimum number of experiments. So we just do them with a single pipe and we just change the pressure, and we know that that's fine. I suppose we could also exchange the pipe out for one that has different roughnesses, and we'd get different behaviors, and construct it. But for simple flow behaviors, and this is the simplest of the flow behaviors, laminar behavior, we can actually get a closed form solution, which is this here, by solving the Navier-Stokes equations. It's a bit involved, so we'll just pluck out the final result, the standard result, and use it. But if we use this standard result, then we get this expression here. And so this term here is the friction factor, which is equal to 64 over RE. And so the equation of this line is just 64 over RE. And so the way in which we'll want to use this is that we will presumably be writing that the head loss is equal to a friction factor multiplied by a length over diameter multiplied by v squared over 2g. The simplest exposition of this HL is on this diagram here. This is HL. Right? If it's Bernoulli, if there's no frictional losses in the system, we can't write that Z1 minus Z2 is equal HL, because HL is equal to 0 in Bernoulli, and Z1 and Z2 aren't the same. So it can't have two different levels if there's no head losses. The very reason it has these two different levels is because there's friction in this pipe that's retarding it, acting against its flow. And so if we come down here, then this is really measured, this is our delta Z in that particular case. And so what we would want to be able to do, presumably we can get, or we'd be able to get this. So if we know what the elevation is between upstream and downstream, we could rearrange this equation to get it in terms of V squared. So if we did that, we would get, and I'm just going up from this, we'd end up with delta Z, which we can measure. We would multiply by 2G. We'd multiply by D over L. And we'd multiply by 1 over F. And that would be equal to V squared. And so if we know what this term is, we know what the diameter of the pipe is, we know what the length of the pipe is. If we know the friction factor, which we think we know, we can get the velocity. But it comes in two different cases, and so we have to be aware of that. And so the interesting thing for us is that we said that at 10 to the 3, so I'm going to make this a bit bigger. We said at 2000, so it's marked on this figure here. This is 10 to the 3, this is 2000, 3000, 4000. So this line here, up through here, well, I guess I should have looked on the diagram. This is laminar flow. This is a transition, and this goes to turbulent flow here. This is transition from laminar to turbulent, and then this is turbulent. And so if we want, we end up having two regimes in which we can solve this system of equations. And I'm probably stealing my thunder from Friday, but let's do it. We know that we can get the velocity if we know this. The other thing that we note is in the laminar regime, friction factor is a function of Reynolds number. It could be a function of relative roughness, but it's not. So it's not a function of this. And in the turbulent regime, so these are the experiments that we've done. So you do a pipe, you flow at one pressure drop, a bigger pressure drop, a bigger pressure drop. Somehow you transition over here, and you have a different behavior. Again, the friction factor is a function of those two variables. Friction factor is also equal to our Euler number, but we won't worry about that. And it could be a function of Reynolds number, and it could be a function of relative roughness. And we see from this that because these curves are horizontal, right, it doesn't change with Reynolds number. So if you double the Reynolds number to go from here to here to here, the friction factor, which is measured off this axis here, is constant. So we know that in the turbulent regime, it doesn't vary with Reynolds number. But it does vary with relative roughness. If you do this experiment in a pipe which is very smooth, so this is the behavior for a very smooth pipe coming down here. So this would be epsilon over d equals 0, no roughness. This is this bounding curve here, that you come down here. If you have a roughness of 0.00005, or if you have a roughness of 0.05, these are all the different roughnesses. So with different roughnesses, the friction factor you might expect grows, right? Rougher, more resistance to flow, and therefore a bigger friction factor. And so the fact that in the laminar regime, the friction factor is proportional to Reynolds number, which includes velocity, and in the turbulent regime, the friction factor is not a function of Reynolds number, which includes velocity, then we might end up with different ways of solving it. So I started drawing it below, but I've got more space here. So I said before that if you rearrange this expression here, so I'm going to write it as this. So if we want to get the velocity squared, in this regime we have a measurement of the head drop between upstream and downstream. We know what planet we're on. We have the length of and diameter of our pipe. We have 1 over friction factor. If we know the roughness of our pipe, say, then we know that the friction factor is going to be equal to 0.072. And so if we want to get the velocity, we just square root this. And immediately we have the velocity. So if we know the head drop, we know gravity, we know the pipe configuration, we know its roughness, we have this. We also have to solve the same equation if we have laminar flow. But if we have laminar flow, it'll look like this, if I just write it out. Same equation, 2g d over L. But now it's 1 over friction factor, and we've said that the friction factor is this. And so if you include this, we would get 1 over friction factor is just 1 over this. So this is Reynolds number over 64. And that's a bit of a problem because Reynolds number includes a velocity term, right? So if we write it out with that included, we get 2g d over L, 1 over 64. And Reynolds number is a velocity, density, a characteristic dimension, and a viscosity. And so it's still equal to v squared, but now we lose one of our velocities. And so we cancel this out, we cancel this out, and so we just have now that the velocity is equal to the remaining terms. And so that's the essence of pipe flow, I think. And it would be density, diameter, and viscosity. So it would be diameter squared, right, in this. And that's basically it. So that's the kind of the trick, I guess, for pipe flow. It's really just a recipe. So I guess all we've done today is we've kind of said that dimensional analysis is a pretty powerful thing because we can figure out what the dimensionless groups of things are, so we can efficiently do experiments, not just in fluid mechanics, but in all of your stuff on campus, any branch of engineering or science. And so we can guess exactly what the format of this behavior would be and show that the Reynolds number and Euler number are the two parameters that control behavior. Reynolds number makes sure that the flow regime is either with or without vortices and is truthful in terms of the flow regime. And the Euler number just gives the forces that are applied to structures. So we have dimensional similitude in both of those parameters. If we know what the equations are for flow in a pipe, we can play around with those to actually define exactly what this friction factor is in the very simple laminar flow regime. And so we can draw that on a Moody chart to be able to show what that is. But if we want to do it for more complicated geometries with turbulent flow and with roughness, we can't get a very simple relationship. But we can run experiments to get this plot, which has been around for a long time. And the essence of this plot is we either have laminar flow or turbulent, fully turbulent flow. And the dependencies of those flows are, for laminar flow, it depends as a function of Reynolds number. But for turbulent flow, it's independent of Reynolds number. You don't get something for nothing. It's now dependent on the relative roughness. And so you can solve for flow in a pipe in two different ways. The same head loss equation, the same friction factor, but a different dependency of the friction factor with the parameters of Reynolds number and relative roughness. And so as soon as you realize that, then you can define two different equations that give you solution for the flow velocity in the system. And it's not that. So the other issue, we've still ignored minor losses, which we'll talk about next time. But we also realize that a problem in this is that the friction factor is a function of Reynolds number, and we might not know that Reynolds number unless we have a best guess of what the flow velocity is, which is what we're trying to find. And so it becomes a problem in guessing a velocity, calculating a Reynolds number for that velocity, getting a friction factor for that Reynolds number, and then checking whether that's the right friction factor to use in the equation when you recalculate the velocity. So it becomes an iterative process. So next time, I think what we'll talk about are the so-called, we'll talk about minor losses, but we'll talk about type 1, type 2, and type 3 questions. So the easiest question is when you get a velocity prescribed. So you know velocity, you calculate Reynolds number, and you absolutely know what the friction factor is. Solve it in one go. If you know the pressure drop or the head drop, then you don't know the velocity, so you have to guess a velocity, calculate a Reynolds number, estimate a friction factor, check whether the velocity that you calculate is the same as the one you assumed. And so it has to be an iterative process. And we'll talk about that next time. And we'll also talk about your favorite subject tomorrow. Okay, great. So that's the essence of pipe flow. It's very formulaic. It's a recipe. We're just trying to understand a little bit about the constraints, and so we'll leave it at that.